Thank you. So thanks again for joining us. And again, anyone who's participating online or in person, just jot down your questions or hand them to Vanessa or put them in the Q&A bubble chat on Zoom. And we are excited to answer those and talk with everyone who's here after we hear from our two presenters who will share their perspectives on glaciers and wine. So without further ado, Jordan, take it away.
Right. Get my screen on here. Okay, thanks everybody for joining this talk. Super excited to be a part of this. Tonight, I'm just going to jump into the research that I've been involved in the past 4 years. If there's something that hopefully it resonates with the wine world, I hope that comes out. In any case, I hope that some of this research that I'm presenting is of interest to everybody out there. And so what I'm going to talk about tonight is how glaciers and watershed characteristics impact stream water chemistry in the Gulf of Alaska. First, what I wanted to do was just give a quick kind of glacier history of the region, so Alaska and North America as well. So the last glacial maximum occurred roughly 20,000 years ago. So glaciers kind of reached their maximum extent around 20,000 years ago. And at this time period, around 8% of Earth's surface was covered in ice. 25% of Earth's land area was covered in ice. And then here in Alaska, 33% of Alaska was covered in ice. Those glaciers started to recede roughly 20,000 years ago. And kind of during the 14th and 19th century, there was what was called the Little Ice Age. And during this time, Alaska glaciers expanded, and they've been kind of receding since the 18th century. And currently in Alaska, glaciers cover around 75,000 square kilometers of Alaska, which is about 5% of the land area. And so this kind of brings us to kind of the big overarching project that I'm involved in, which is the Alaska EPSCoR Fire and Ice Project. And most specifically, I'm involved in the Glacier Margins team, which is looking at climate-driven changes to nearshore ecosystems and organisms in the Gulf of Alaska. And even more kind of specifically, I'm involved in really nailing down this first goal of the Coastal Margins team, which is to characterize the hydrological and biogeochemical dynamics of rivers along a glacial to non-glacial watershed gradient and their linkages to coastal oceanography. And what I wanted to dive into is why is this important for us to understand, and give a few slides of why I think this is important for us to understand as a kind of a scientific community and kind of the public at large. And so over the past couple of decades, there's been a real concerted effort to understand the current and future freshwater flux to the Gulf of Alaska. Currently, about 50% of the fresh water that enters the Gulf of Alaska is derived from glaciers and ice fields. And in this Gulf of Alaska region, about 800 cubic kilometers per year of fresh water enters the Gulf of Alaska. And kind of some perspective, that's more than the Mississippi River discharges. And the Mississippi River watershed is about 6 times the size as the Gulf of Alaska region. And so this region here in Alaska is very important in terms of the freshwater flux to the Gulf, as well as nutrient fluxes to the Gulf. And so in the Gulf of Alaska, so some climate models have predicted by 2100 that precipitation as rain is going to increase, snowfall will decrease, Glacier input is going to decrease roughly 34%, and autumn and winter runoff is going to increase due to increases in rain during the fall and the winter. And so these changing seasonal patterns in the climate is going to change the timing of freshwater nutrient fluxes. And also glaciers, they mediate the seasonal discharge of fresh water. So there's a really nice way that glaciers impact, the seasonal cycles of fresh water that's discharged to the Gulf of Alaska. And they also mediate water temperature and many other water properties. And so what we know about the chemical composition of glacier-fed streams is that it's very distinct from non-glacial fed streams. And so these streams have a high dissolved content of potassium and low dissolved silica compared to non-glacial fed streams. And glacialized streams, their dominant ions are always going to be calcium, bicarbonate, and sulfate. And they always have a high ratio of calcium to silica and low ratios of bicarbonate to sulfite. Glacier-fed streams also have high sediment concentration and high sediment yields. And so I like to kind of think about this as they are like these super efficient transporters of nutrients to downstream ecosystems. And so how do we achieve our goal of understanding the hydrologic and biogeochemical dynamics of streams in the Gulf of Alaska? And so underneath this EPSCoR project, we've chosen 2 regions within the Gulf of Alaska. So one region in Ketchikan Bay, which is in South Central Alaska, and another in Lynn Canal, which is in Southeast Alaska, near Juneau, Alaska. And in each of these regions, there's 5 different stream sites that we study. And they're set up so that they are along a gradient of glacial coverage, so high glacial coverage to non-glacial coverage. And so the research that I'm involved in and the fieldwork that I'm involved in is in Ketchikan Bay. And the Lynn Canal stream team, they do a similar set of studies each month, like we do. And so in Ketchikan Bay, we have our 5 stream sites. So the Gruink, Halibut, the Wazinski, Tutka, and Jackaloff. We utilize the Kositsna Bay Lab, which is a NOAA and UAF laboratory where we base out of often. And so the Gruink watershed is highly glaciarized, and the Jackaloff watershed is non-glaciarized, and the stream is primarily fed by precipitation. And so how we accomplish our goal is we go and we visit our stream sites once per month from around March or April to October. And we've been doing this since 2019. And this summer is our last field season for this project. And so when we go down there, we measure stream discharge, pH, alkalinity. We get precipitation samples and we gauge how much precipitation has occurred on a monthly basis. Then we also do water sampling. So we grab water samples and we bring them back to the lab and we analyze them for water stable isotopes, cation, anions, suspended sediment, the alkalinity, and then organic carbon. So dissolved organic carbon, DOC, and POC, which is particulate organic carbon. We also have data loggers that log stream height and specific conductance, as well as stream water temperature every 15 minutes. And so just a few field pictures. So this is the lab that we often are based out of when we're down doing our field work, the Kissins Bay lab. Here we are measuring discharge by pack raft. And so we have an acoustic Doppler current profiler that we connect to a pack raft, and we vary it across the stream. And this is one of our methods for getting discharge in some of our larger streams. And then when it's lower flow, we do manual discharge measurements with a handheld flow meter. Here we scrambled our way onto the brewing glacier, and we grabbed ice samples and superglacial water samples. We do a lot of sampling by pack raft, so we try to do longitudinal studies or sampling campaigns where we start at the headwaters and float down the stream and take samples along the stream all the way to the ocean. And this allows us to understand how the watershed contributes differently to the dissolved and suspended load within the stream. And then this is just a couple pictures of our gauge setup. So in these PVC wells attached to fence posts, we have our stream height sensors and our conductivity loggers that we install in the spring, and then we take them out in October. And so I just wanted to just briefly talk about like why we measure what we measure. So the first thing, one of the most important things that we measure is discharge, and discharge allows us to understand how a watershed functions. So the watershed hydraulics, and the discharge is one of the primary drivers of the nutrient fluxes to downstream ecosystems. We also measure stream temperature, and stream temperature allows us to understand kind of this connection between climate, glacial coverage, and then groundwater sources to the streams. And many species kind of rely on stream temp to survive, and stream temperatures are very well mediated by glacier melt. So moderately glaciarized catchments are their water temperature is very well mediated by glacier melt. And we also measure pH and alkalinity, and pH is very important in controlling chemical speciation. So this is important for our geochemical modeling. And also trace metals are very sensitive to the pH and also other redox conditions. And aquatic plants in these streams really thrive in circumneutral pHs. And we also measure alkalinity, and alkalinity is this measurement of the buffering capacity of water. So that means how much of a pH or a base can you add to the water, and the water stays, the water pH stays relatively constant. And then kind of continuing on what we measure and why we measure, the cation and anions help us, as well as silica, help us understand, what material the water interacts with. And there's a myriad of other things that can be used, but it also helps us to understand different flow paths water is taken to reach the stream. And water stable isotopes help us track seasonal changes of water sources. So how much precipitation compared to snow melt, compared to glacier melt, compared to groundwater, how those change through the season. A really important parameter that we measure is the total suspended sediment. And this helps us understand the transport of terrestrial material, both organic and inorganic material, to the ocean, and also helps us understand micronutrient transport to downstream ecosystems. And then finally, dissolved organic carbon, particulate organic carbon. And then we also measure a stable isotope of carbon-13 of the particulate organic carbon. And this allows us to understand the type of organic carbon and the sources of the organic carbon. And knowing this is, and these things are really important for downstream ecosystems, and also kind of on a broader level, understanding global carbon cycles. Okay, so what we wanted to do, and what the rest of this presentation is focused on, is some work that we've done previously to understand better the context in which we're collecting our data. So before we really dug into the data that we've collected in Kachemak Bay and Lynn Canal, we wanted to provide some context for our newly collected data. And so what that kind of looked like is we dug into USGS data that had been collected throughout the Gulf of Alaska. So we ended up choosing 34 stream gauge sites across the Gulf in order for us to kind of test hypotheses kind of at a broad level before digging into our small regional studies. And so, like I said, we used 34 stream gauge sites, USGS stream gauge sites, historical data and modern data of stream flow and water chemistry. We grouped them into 7 distinct hydroclimate regions across the Gulf of Alaska. And then we calculated the yields of the solutes and the yields of total suspended sediment. And then one of the more important things that we did in this work is look at concentration discharge relationships. So CQ relationships are concentration discharge relationships. And that is looking at the relationship between this ratio between the concentration and the discharge in log space, and looking at the slope of that relationship. And this slope has a physical interpretation that helps us understand the workings of a watershed. And so what we did is we looked at physical watershed characteristics first. And so we calculated the climate regime of a watershed, glacial coverage, geology, forest coverage, and stream discharge. And then we used the total suspended sediment versus the total dissolved solids to kind of create this understanding of a relative weathering index, which is kind of this index between physical versus chemical weathering. And we looked at the ratios of bicarbonate versus calcium, and then bicarbonate versus silica to help kind of constrain carbonate versus silicate weathering within a watershed. And then finally, we looked at concentration discharge relationships compared to watershed characteristics. And so trying to figure out what watershed characteristics best describe the variation that we see in concentration discharge relationships. And so, like I said before, the slope of the concentration discharge relationship in log space has a physical interpretation. So for example, if we're looking at the concentration of calcium, as discharge increases in the stream, if the concentration of calcium decreases, we say that it's there's a dilution factor. So a slope of concentration versus discharge close to -1, we say that there's a dilution factor. And continuing on, hemostasis is a term where if the concentration of calcium, for example, does not change much as runoff or discharge increases, we call that hemostasis. So the concentration stays unchanged as a function of runoff. And finally, there's an enriching example where if runoff or discharge increases and you also have an increase in concentration, there's an enrichment of that element of interest, which means that there's some sort of reservoir within the watershed that is captured in when discharge increases and is then flushed into the stream. And so, first of all, what we looked at here is the total dissolved solids. So this TDS, or total dissolved solids, is the summation of the major cations and silica in terms of yield. So the flux weighted by watershed area. And then on the x-axis, we have total suspended sediment yield. And we put all the data that we collected from the USGS onto this plot. And so on the left-hand side of this plot, the stream is exporting most of its load in the dissolved phase, whereas on the right-hand side of this plot, the stream is exporting relatively more of its load in the suspended phase. And so what we found is that in glacier-fed streams, on average, they're exporting most of their load in the suspended phase and less so in the dissolved phase. And essentially what this means is that you have much more physical weathering happening compared to chemical weathering within the watersheds. And in these streams, you have this suspended sediment, which enters the ocean and can, in the ocean, as the salinity changes compared to the stream, you can actually have a release of different micronutrients into the ocean, which that can be utilized by primary producers within the nearshore ecosystem. And kind of secondly, what we looked at is this comparison between carbonate versus silicate weathering. And kind of the main idea here is to understand how solutes are being generated within watersheds, and then also understanding what is controlling the overall geochemistry of the streams. So what we found is that the majority of streams within the Gulf of Alaska are weathering carbonates, and the minority of streams are weathering silicates. And also what we found is that of all the streams that we looked at, the non-glacialized streams, only the non-glacialized streams kind of fall within this silicate region on this plot. And this has a lot to do with kind of the kinetics involved between carbonate and silicate dissolution. And kind of from this, we can also understand, what is controlling the alkalinity and the pH of these waters in terms of these chemical weathering regimes. And kind of finally, and most importantly, what we looked at is the geomorphology and glacial coverage controls on the different solutes. So what we found is that solute generation, or the concentration discharge relationships, are mostly controlled by watershed geomorphology. So the slope of the watershed, elevation, and relief. And overall, the glacial coverage has very little effect on concentration discharge relationships. And solute yields are most significantly influenced by glacial coverage. So the more higher watersheds with higher amounts of glacial coverage export more solutes compared to like a non-glaciarized catchment. And the streams within the Gulf of Alaska follow a similar trend across a global compilation of watersheds with similar glacial coverage. And so after all that, what's the big picture here? So as glaciers recede, we're likely to receive decreased solute flex. However, we kind of hypothesize that solute generation may remain constant, and we're going to see a shift from high suspended sediment to, or in other words, high physical weathering to a more chemical weathering dominated system. And so kind of like to think about this in terms of like the nutrient transported to the ocean. So looking at this in terms of that, lower suspended sediment is probably going to lead to less micronutrients transported to the ocean. And so that was kind of a big picture look at what the first half of this project has been accomplishing. And then what's coming up next is looking at compilation of data from Katchmack Bay and Lind Canal under the context of hydroclimate gradient, and looking at the detailed seasonal cycles of stream chemistry, so the changes in concentration and yields throughout a melt season. And then further down the road, chemical weathering models, so further kind of investigating the controls on inorganic nutrient fluxes to the Gulf of Alaska. And that is that. And I'll turn it over to Cara.
Whoa.
Yeah, thanks, Jordan. That was deep into the science, and now we get to hear a little bit more about well, I'm not going to spoil it. Cara, I'll just work on turning your video back on.
Oh yeah, please. All right. That is something that was very, very,
Okay.
there we are. That was very, very interesting. And I would like to pretend that I understood 10% of it. But thank you, that was so cool. And when we first started talking about this, I really was a little nervous about how do we kind of turn this into a conversation about wine. But sort of how you talk about the movement and the melting and how it pulls different like nutrients and changes the composition of the soils throughout the area into the waters, really reminds me of everything I have been studying about wine for a lot of different regions. So sommeliers, we're not scientists, however, at all, but we do follow a lot of science, sometimes at a more base level than we need to. But you know, we always make this joke that sommeliers we are geologists, we're climate scientists, we are weathermen, we are, you know, agriculturalists. All of these sort of little things really go hand in hand to actually get something in your glass. And as I started reading more about glaciers, I was reminded of how many wine regions in the world are super affected by glacial movement or the floods that ice melt from glaciers has created. So I guess I'll talk about a little bit about that. And please, Jordan, at any point, like, interrupt me, tell me if I'm wrong, correct my pronunciation, add to it, because I only know a little bit. And most of it is not something I think about on a day-to-day basis. Okay, now I'm going to share a few little pics, if that's all right with you. Okay. Oh, here we go. But I don't want it to only be pictures because not everything I'm doing is about pictures. Okay, so I wanted to show this pic of old ice sheets in North America. So, we were talking about Alaska. So I wanted to kind of talk a little bit more about something closer to Alaska. We don't really have fine wine regions in Alaska yet. Let's see what happens in like 1,000 years. But this is what North America kind of looked like, right? The Cordilleran ice sheet is kind of Cordilleran, thank you, is a little bit of what I want to talk about. And then I don't know if you can see my cursor, but I'm going to talk about this little area here of Washington State and Oregon. So back in the 1920s, there was a geologist named Bretz who was trying to figure out what was the deal with the channeled scablands of eastern Washington and parts of Idaho and Montana, these areas that were just kind of like ripped apart, but not in your typical sort of slow erosion over time way. And he and another scientist from the National Geographic Survey, they kind of went back and forth with their hypotheses to kind of figure out like what is going on here. So there's the ice sheet here right above and part of northern Washington into Canada, as well as in Idaho and Montana. Okay, so this was a continental glacier that was believed to have melted relatively quickly over a course of 4,000 years. So the melt off of these ice caps created a huge glacial lake, which you can see here, called Lake Missoula, which is where modern day Montana is, northern Montana. This lake was sort of your kind of like normal glacial melt, right? However, the ice sheet kept sort of creeping further and further south, and the ice blocked Clark Fork River, which is also in northern Montana, and it created a bit of like an ice dam. So the water wasn't really able, from the lake, wasn't kind of able to do its normal, like make its way towards, I guess, the ocean. And as the caps kept melting, way too much water started building up in this Lake Missoula behind the dam. And then since ice, of course, is less dense than water, when the water level got too high, the ice sort of rafted, floated upwards, and the melted water started pouring out beneath it. And it came with such pressure that it eventually broke the dam, and this entire lake drained incredibly quickly. The rest of this ice sheet was sort of blocking its path north, so it had to be forced sort of southwest. Okay, it created hundreds of river channels very, very rapidly because these giant waves that were formed, they say it was about 2,500 cubic kilometers of water, or half of Lake Michigan, sort of broke free, lifted boulders, just carved through these cliffs and hills, created the channeled scablands, created the Spokane Valley, the ancient Lake Lewis, And when the route hit little log jams, kind of, you can even kind of see them here, it would spill out into these even bigger, like new lakes, which created new valleys, which is, you know, the major one now is Columbia River Gorge, which separates Washington, Oregon, and the Willamette Valley, which is nestled right here in the bottom left, between the Oregon Coast Range and the Cascades. And they say that this happened many, many times, about like maybe every 60 years over a course of 7,000 years during the late Pleistocene. So something between 28,000 to 13,000 years ago. And it basically changed the landscape completely of the Pacific Northwest. It was kind of interesting reading about this because it sort of reminded me a little bit of like Always Sunny, when it was like science is a bitch sometimes, because nobody wanted to believe Brett's. He was talking about like a catastrophic event. And, you know, we're at sort of a point in science where it was like, everything that we see, we can explain because we can see it. We can see the effects of erosion. We can see the effects of earthquakes. We can see the effects of lava flows. The idea that like a huge asteroid would hit and cause, you know, massive climate change, or that a big dam, an ice dam would break and completely change hundreds of thousands of miles of land, was a little bit like old thinking, a little bit Bible sounding. So it took him about 40 years to actually get this published and accepted. But I'm going to show you next. You can kind of see here. So the dark blue was Glacial Lake Missoula. The light blue was the path of the floods. And then you go and you kind of look at modern Washington wine country, and it's basically the same. So you get all of these rivers, and all of these valleys to the east of the Cascade Mountains, and it went down into the Columbia Valley, and then along the Columbia River and down into what is now the Willamette Valley. Eventually, these lakes, these giant lakes, after all the 7,000 years of this kind of constantly happening over and over, drained out, right? And things kind of dried up. So when the massive flooded regions began to drain, what remained was hundreds of feet of sedimentary soils, which covered what was once basalt bedrock, so remnants of volcanic activity. And this created really fertile landscapes for all sort of crops, including wine grapes, right? In both Washington State and Willamette Valley, and a little bit in Canada too, in the Okanagan Valley. So if we go back really quickly and look at Washington, so most of our fine wines are grown all over here in this sort of the treaded path of the Missoula floods from Lake Missoula, from this big glacial melt. And we're kind of lucky that it created so much very like nutritious sedimentary soils here, because this area is like an arid hellscape, harsh climate for wine regions. They only get, so the Cascades create a major rain shadow, and you only get about 8 inches of rain a year in some of these areas. But luckily, you have these very nutritious soils, and with a little bit of drip irrigation over here, you can actually create a really healthy yet low yielding wine industry. When you go, so you'll see that all the wine regions are basically along the rivers: Walla Walla River, Yakima River, Snake River, and Columbia Rivers. It's all mostly sedimentary sandy loam vineyard soils over basalt. Now, when we go into Oregon, Oregon is a much cooler region overall, because now we're on the other side of the Cascades, outside of Columbia Valley here. We're on the other side of the Cascades. We're really talking about fine winemaking in the Willamette Valley. So yes, tons of super fertile soil. landed here as well. But you can kind of see that the major wine regions, the highest quality regions, really, the dark green ones here, these are all on the western side of the Willamette River and in the foothills of the Coast Range. That's because this is a much colder place. And so when you have a little colder climate, you don't really want too nutritious of soils. You want your vines to struggle a little more. So they do a little higher elevation. The soils here are very free draining, but at the bottom, it's like these thick, jory soils that they're called. And that is sort of a reddish clay silt soil that's a culmination of colluvium sediments that have over time continue to come down the mountains, as well as the weathered basalt bedrock plus like organic matter. And all of this formed due to the sediment that was carried from the ancient Missoula floods. So Washington and Oregon were created as a byproduct of the glacial movement and melting, but glacial movement itself, glaciers actually moving, has influenced the wide regions of the world. Usually what you find in those regions are morainic soils, which is the debris of melting glaciers, things kind of moving around. It's like a mix of cool stuff, lots of sand too. And then combined with the right climate, it creates excellent conditions for fine wine production. So one of our most famous ones is the Finger Lakes in New York State. That was carved by insane glaciers. I believe the Wisconsin glacial episode 22,000 years ago, where glaciers 2 miles thick carved out these narrow parallel lakes. And in an area which could be otherwise, you know, kind of wheat, potatoes, not exactly fine wine, you know, these huge lakes help moderate temperature. In the summers where it can get really hot and humid, there's actually like a light, you know, these lakes are so big and deep, they can create really good breezes. In the winter, the areas right around these lakes, although they get snow, they're not as like deeply frozen and frost prone as sort of the outlying areas. So you can grow some really beautiful grapes like Riesling, Cabernet Franc, Pinot Noir. When we go into France, we're kind of here in southern France, the Rhone Valley was carved by the Rhone Glacier. And we have insane soils here. There's a lot of granite, but you get these galettes, which are only found, I'll show you a little picture here. Look at these stones. These are only found in this one area, and they were fully like deposited by movements of glaciers. These aren't, nowhere else around it except for this area has these huge soils. These were not placed there. This is what the vines grow out of. Another glacier carved out Lake Geneva. This is kind of like a really intense topographical map, but up here you kind of have like the Jura Mountains, and Lake Geneva's up here somewhere, but then it also carved out areas into above the Ligurian Sea, which we'll look at here. So the basin of Lake Geneva is a part of what is now the mountainous region of Savoie in France. And then in Italy, we have, okay, so here's Lake Geneva, here, up here, and then you get into the Alps, and the Alps had a whole ton of glacial activity too. And glaciers sort of pushed their way down and through this whole area, creating the Po River Valley, creating Lake Garda, Cuomo, Lake Garda's over here, and creating all of these really insane rivers from Piemonte all the way to Friuli. And if any of you drink Italian wine, and if any of you have ever studied Italian wines, we were always talking about morainic soils. And I kind of didn't really understand it as much as I do now about how much that really meant. No, actually glaciers moved through here and left sediment. I was always thinking it was more like marine soils. And I was like, oh, maybe it was like under the under the sea at one point. Now, glaciers like bulldoze their way through here, creating these valleys, which now make like some of the best wines in the world. You get really beautiful Nebbiolo from Piedmont. You can get beautiful Riesling and Pinot Gris in the glacier formed area of Alto Adige, which is right at the base of the Alps here. This whole valley was carved out by glaciers. Then you get to this area of Lake Garda, which is a glacial formation as well. I mean, look at this. If it wasn't for a glacier moving through here, would we ever have these like incredibly, gorgeous, but also fruitful areas of fine wine? It's really, really, really amazing. So the next time you are drinking wines from Alto Adige or the age-worthy champagne-like wines from Lombardy called Franciacorta, or the easy drinking Proseccos or Sauvignon Blanc or Pinot Grigio or Tokai from Friuli, you can thank a glacier. You also have something kind of interesting, a Patagonian ice sheet, which I believe is still a thing in the Andes. And some areas in Chile can dry farm, meaning they don't need any irrigation, even though they're kind of high elevation valleys, because they're still getting ice melt as a natural irrigation, especially, it's just kind of crazy all in here. And then finally, this was the last thing that I thought was really weird and really interesting. I just want to go down to Australia really quickly. I don't really understand a lot what I read about this in South Australia in Adelaide's Mount Lofty Ranges, because I kind of thought like Pangaea was like the supercontinent, and then there was like 2 or 3 before that, which I just, my mind is really blown recently. It's really intimidating to try to say this back to a bunch of scientists. But in South Australia, the region of Adelaide's Mount Lofty Ranges has given some very extreme evidence of glacial involvement. So some vines here are planted or rooted in soils atop 750 million year old rocks that accumulated in what was called the Adelaide Rift Zone, which dates back to when the pre-Pangaea supercontinent Rodinia began to fragment. And I was reading some things in Earth magazine, Earth Journal, that there's evidence that this fragmentation began an era of the so-called snowball Earth episodes, where the Earth sort of repeatedly had such extreme glacial episodes that it almost like froze over. But then this area was continued to be heavily impacted by tidewater glaciers during the Marinoan glaciation event, and just more of them over the next hundreds of millions of years. And you get some really gorgeous wines from down here too. So, you know, it's just kind of cool that we can drink wine that is rooted literally into the oldest soils of Earth, like we see right here, and ancient glaciers, along with seismic and volcanic activity throughout the eons, have created landscapes, terroirs, and everything that sort of happenstance and the beauty of the biodiversity of this planet created the wines that we can drink today. So I'm gonna have to take some more science classes, maybe over the summer at City College, because I wanna understand a little bit more about all the things I read. This is a very layman's way of explaining these things back to you. I hope that helped.
Was awesome. Yeah.
That was amazing. Yeah. Sorry, go ahead, Jordan.
No, I was just saying that was pretty awesome.
I believe you're being recruited, Cara. We have someone searching for more PhD students and wondering if you're interested. Like, don't be.
Listen, if you can find someone to pay my way, I don't make much as a wine shop owner, okay? Let's do it.
Well, you could see the pub there for a minute. Science pays.
Science pays.
Well, I'm gonna thank a glacier for that.
Yes, I'm drinking I'm thanking a glacier for this wine from Italy.
So we have a little bit of time for some questions and answers. Vanessa, do you want to start at the pub? Anyone there? I've got some in the Q&A up here, but.
Anyone in the pub wanna jump in? People are munching on nachos.
Yeah.
Okay, got a question. And if you wanna stand, they can see you.
Okay, I was wondering if there's any glacial activity that's impacted the wine regions of Northern California, specifically Sonoma is what I'm curious about.
That is an awesome question. So as far as glacial activity, I couldn't find a ton of hard evidence about that, but Northern California is completely impacted by seismic and volcanic. So if we think about, oh, I wish I had more slides. If we think about when the Pacific plate and the North American plate slammed into each other, it basically pushed up this just big slab of continent, and it pushed it all the way up over time, creating the Baja Peninsula in California. It created Santa Barbara, it created that really beautiful kind of cove that we have in Southern California. And then it just smashed land together in so many different ways to create all of the valleys and then river systems. There might have been, because you know, our mountains in California are like not as old as a lot of these glaciers, I believe. And it's mostly volcanic and seismic for sure. I mean, even if you're driving through Napa Valley, for example, when you are driving up, let's say the Silverado Trail going north through the valley, on your right, you have the Vaca Mountains, which are like decomposed volcanic material. And on the left side, you have the Mayacamas Mountains, which are all just like organic material, you know, sedimentary rocks and things like that, because that was pushed by the plates, whereas the other side was formed by volcanoes. And then I think all of the waterways came less from glaciers and more from like the impact of these new high elevation mountains throughout the Sierra Nevadas and everything like that, that became snowpacks, which then melted and things. I'm pretty sure. Jordan, do you know more about that?
Yeah, no, you did a really good job with that. So just looking at this map, during the LGM, most of California was not impacted by glaciers. There was some glaciation here, kind of I guess east and central California region. So that's kind of where you have the like Half Dome and those areas. So
right,
that area was uplifted. Those plutons came up and were uplifted, and then during this glacial period, those were kind of eroded away, and that's where we see those glacial valleys now, half domes.
They were glacial valleys.
Yeah. So, but nothing really on this. You know, I don't exactly know where Sonoma. I haven't been there yet.
So there's Sonoma's right above your little.
So nothing. Yeah. Nothing in terms of glacial activity there.
And that area over where glacial activity was in California, like that Yosemite area, that is not wine region. That is like super extreme terrain mountain region. That valley that's to the left of that dark blue slice, which is the Central Valley, you know, America's like fruit basket. That was a result of the all the plates being pushed and creating a deep sort of crevasse because of that. And that's why it's so fertile, because it got flooded. Good question. Damn. I'm gonna like look on Wikipedia to answer some of these things.
Thank you. Did we have another question here in the pub? Okay, Victoria.
Hi, I have a question for Jordan. My degree's in history, so I understood next to nothing from what you said. But I got curious about when you were talking about sediment and the temperature of the water. Because as somebody who's gone to Chittenden a couple of times and gone fishing, I think about if I fall in that river, I'm a goner, there's too much sediment, I'm gonna drop. I'm just wondering if like the temperature of the water changes the amount of, like you had talked about chemical disintegration versus physical, and I'm wondering if temperature plays a role in that, if that makes any sense.
Yeah. No, I think, yeah. So the role of like water temperature in chemical weathering, and that idea is, those are pretty well tied together. The temperature of the water can control the kinetics in which chemical weathering takes place. And so, for example, in like a non-glacial fed stream, you're going to have relatively warmer water within that stream, and you're likely to have higher chemical weathering. And so you might find higher concentrations of dissolved elements within that type of stream compared to a glacial fed stream. And so water temperature plays a very important role in that kind of chemical weathering, within the chemical weathering regime of a stream. And yeah, I think, does that answer your question? Perfect. Gotcha.
She said, yes, it does.
Awesome.
I have a question, Jordan.
Yeah.
Can you tell, you mentioned you were talking about the chemistry of, okay, the chemistry of the soils as glaciers melt. Does it change? It changes like the pH of anything? Like, I'm just wondering, I'm thinking a lot about all of the glacial regions that are now wine regions, and we tend to have sort of lower pH soils, I think, and you tend to get a little higher pH wines. And grapes like to be sort of between 5.5 to 7. Do you think that over time, that is what is like the glacial movement may have affected those soil pHs in those areas?
So I'll preface this by saying that I'm not a soil scientist, but from what I understand from a glacial stream, or like kind of a glacial history point of view, within like a stream or like a watershed that is heavily glaciarized, you'll see extreme water pHs. For example, in the streams that we are working in Kachemak Bay, stream water pH ranges from the mid 7s to 8.2 or so. And that has a lot to do with the geology of the region, and also has a lot to do with, especially in the heavily glaciarized watersheds, the sediment can actually, it's called absorb, so it can absorb hydrogen ions onto the actual particle. So pH is a measure of the concentration of hydrogen ions within water or whatever you're measuring. And so that can actually act to raised the pH. And now, kind of contrastingly, in the Lynn Canal study region, that is a different geology there. So there's more igneous rocks, so more like granites, for example. Whereas in Kashmak Bay, there's more of these sedimentary rocks that basically were kind of on the margin of old like ocean shores, and then thrust up as the Pacific plate hit the is being subducted. And so getting back to the Lynn Canal in Southeast Alaska, which is kind of weathering more igneous or granitic rocks, those water pHs are lower compared to what we are measuring in Kashmak Bay. And that is geology, and also they have in Southeast Alaska more developed soils and more developed forest within that region, which can act to lower the pH of the water, of the stream water more. And in terms of like the soil, I don't necessarily think that the glaciers have a ton to do with the actual like pH of the soil, other than they, the movement of the glaciers form like the space that the soil can form. So I think the pH of the soil has more to do with like the geology within the region, and then also kind of the overall like weathering, or more, this comes back to more the chemical weathering of the soil, and that history. So whether it's been highly weathered or it's in a climate where there's a little less precipitation and more moderate temperatures, there's less chemical weathering that happens in those areas.
Wow, very interesting. Thank you.
Yeah, cool.
Yeah.
Thanks. I've got a couple online questions I wanted to knock out. Cara, one seems very wine specific. I don't know if you can see it in the chat, but it says, do you have much experience with pre-Blanc wines? Is it the height or terroir that makes it so good?
That's a good question. Yeah, Pré Blanc is it's a white variety that comes from like far alpine north Val d'Ast in northern Italy in the Alps. I think it really has, I mean, I don't know for sure, but I would say that for any grape to be able to survive that kind of like extreme terroir, which is frosty, windswept, alpine, snowy, ski country. I think really it's just a matter of a grape that can really adapt to its surroundings. So it's something that is kind of round for how alpine it is. It's not as horribly like, it's a very linear wine, but it's not like a super sharp, awful, acidic razor blade, like some grapes that are grown in the mountains can be. But, I think it's slightly related to the Pinot Noir family. And I think it's probably something that over time kind of crossbred with other little grapes up there, and really is a product of its terroir. But definitely its elevation is a huge part of it. I mean, this area in Morges and La Salle in Val d'Ast are like some of the highest vineyards in Europe, like 4,000 feet up. So yeah, it's definitely, I think, that's very cool. This must be a little wine geek if they're talking about that grape. Like 4 people know what that grape is. Amazing. I like that. We sell some if you want some. DecantSF.com. But very chocolatey, very, very lovely. But it does. So here's one thing really quickly about really high elevation wines. Even if they're in extreme cold temperatures, high elevation, even though you get, I think like every 100 feet you go up, the temperature drops by a degree in Fahrenheit, like comparative to sea level or something like that. But what you get is a ton of UV. And so when you get a lot of like unfiltered sunlight, because they are above any sort of like fog line or cloud line when they're that high up most of the year, you get a ton of UV, and the skins can tend to be a little bit kind of like, they kind of mutate to be a little bit thicker. And so you get a lot more phenolics out of those skins as it actually gets ripe from just like pure unadulterated sunshine. And those grapes are struggling so hard. They are not putting a lot of effort into their green, their greenage, their foliage. They're all putting it towards the fruit. And so you can get some really deeply concentrated grapes from that, with a lot of ripeness, which is kind of cool. I hope that answers a little bit.
Yeah, that's fascinating too, just to hear the contrast between, these wines regions that have been flooded up to the, getting the contrast of what's up high. So thank you. And it looks like, they really appreciated your insight.
So the grapes that grow in these glacier regions are a lot more forgiving than any grapes that are grown in the mountains.
Interesting. The other question I have for online, thank you to those who submitted. I've kind of combined a few questions in some cases, but often people, this one's a little more for Jordan. Often people refer to glaciers as conveyor belts since they deliver materials as they flow and melt. What do you think will happen to the waters of the Gulf of Alaska as the ice recedes and eventually is all melted? And I would like to put a disclaimer on here that we will not send this to your PhD committee. We are just looking, you do not have to be, we won't judge you if this doesn't actually happen in the next 1,000 years. Your best guess.
Yeah, no, it's it's one that I think more about like what's going to happen to the stream water compared to maybe what's going to happen to the Gulf, like the ocean water in the Gulf of Alaska. But what I do know is that currently the within the Gulf of Alaska, the freshwater discharge drives what is called the Alaska coastal current. And so that's this current that runs from southeast Alaska, this map. I'll just pull up the map here of Alaska. So the Alaska coastal current runs kind of from southeast Alaska along kind of central Alaska and then down to western Alaska. And some of the water that originates here in the Gulf of Alaska from glacier melt actually can end up getting entrained in the currents that come up and feed into the Chukchi and the Beaufort Sea. So kind of in terms of like oceanography, like an oceanography sense, which I'm not by any means an oceanographer, there will be significant impacts to that ocean circulation pattern as less fresh water enters the ocean from the Gulf of Alaska. And kind of in terms of the stream water, we're going to see, we'll see stream or river water that's probably going to have less sediment and is going to have kind of a different chemical composition than what is in it today. And kind of what we're trying to figure out, with the EPSCoR project It's kind of linking like, right, so we have really highly glaciarized stream. And what does the biology look like in the downstream ecosystem in that watershed compared to a stream that is not glacial fed? And how does the biology in that stream look compared to the heavily glaciarized watershed? And so those are the kind of linkages that we're trying to figure out now in order to maybe, better hypothesize what may happen to nearshore ecosystems in the future as, glaciers recede to a point where the meltwater is no longer really a large contributing factor to the overall discharge.
Can I ask a question? Is fresh water, like drinking water, from glacial melt something that is important to like the people of Alaska, or is it more to like wildlife?
Well, here in Anchorage, majority of the public drinking water is sourced from glacial melt. So
Yeah.
and
Okay.
yeah, most, the vast majority are I think over half the population of Alaska lives in or around Anchorage. So in Anchorage, we rely on glacial meltwater as a huge source of our fresh water. And like also on top of that, hydropower is a huge thing in the Gulf of Alaska, which is, really tied to glacial meltwater is what, powers a lot of the hydropower.
Wow.
So lots to think about.
Yeah.
Yeah. I thank you for covering so many topics and even being willing to go a little past time. I think no big deal, but that's what we wanted, was a good discussion. So I want to thank everyone who submitted questions online in the Zoom. I believe that they might have turned off the video at the pub just because sometimes internet can get spotty. I don't know if that's just an Alaska thing. Let me know, Cara.
I'm good.
Okay, excellent. Yeah, I'm good here. But yeah, I just want to thank everyone again. Hopefully they can still hear us and see us. And I want to also thank Vanessa, who's been running things at the pub. She's with Telesom, and okay, awesome. They're back. Oh, do you have any more questions? Any final things to send us out?
Anyone? Any other questions for our two experts, Jordan and Cara? No. All right. Oh, super grateful is one comment from the crowd. People are starting to head out, and I know we have an open mic. I wanted to thank everyone, especially Cara and Jordan, for sharing your knowledge with us. It's been absolutely fascinating. And Courtney, thanks for organizing this. So I'm from Telesom, and before we wrap up, I did want to say that we have an event on April 16th with Ice Age Charcuterie, and we have Sunny here in the audience. So it's a charcuterie and wine pairing event. And if you like Cara's work, you can follow her on Instagram. She has lots of like educational content, videos, cool stuff. Jordan, I don't know where your Insta is. Like, is this a private thing?
I'm on there. I just, it's all baby pictures and stuff.
And hardcore.
I'm on there. I'm on there personally as Cara Patricia SF or Decant San Francisco. We post lots of fun stuff, and you can always reach out to me too with any of your little wine questions. Just DM me.
Awesome. Thank you all again. And unless we want to stay on for an interesting open mic, I guess we'll sign off.
Well, here's Wonderwall.
Yeah. Perfect. All right. Thank you again.
Great night. Thank you. Bye-bye.
Thanks, Cara. That was awesome.
Bye.
Yay, thank you. It was so informational.